Okay, so good morning, everyone. We are recording now. So let's start from where we left off yesterday. So we were discussing, well, yesterday we defined what a dual of a plane graph is, right? And I made one lapse that I want to correct. So at some point we discussed that the dual of the dual is the original graph so long as the original graph is connected. There is a caveat here. The dual of a plane graph, as we defined it, is an abstract graph. So you can't really define its dual because we did not define the dual of an abstract graph. So in order to make this exercise valid, we need to define the plane dual of a plane graph. And it's basically the underlying abstract graph will be the same. The only difference is that we need to get a planar embedding of the dual so that we have a plane dual, and then we can define its dual. Otherwise, it's invalid, right? As we discussed it. So, okay, so that means that we need to define the plane dual. And let me just go back to this example here. In fact, the way I defined the dual graph, I did it by example. And that example tells you how to get the plane dual. So the idea is you put a vertex inside every face, right? So it's basically the way we did it here. The red colored graph, if you consider its planar embedding, then it is actually, let me put some cloth here. Okay. Okay, the red colored graph, if you look at its planar embedding, that is actually the plane dual graph. And so what it means is that you want a planar embedding. And the idea is you put a vertex inside every face of the original graph. And then you join those new vertices, the red colored vertices, which correspond to faces of the original graph. You join them by an edge so that whenever two faces share an edge, they will be joined, and that red colored edge will cross the corresponding black colored edge in the original graph, right? So again, we are not proving that if you do it this way, you will get a planar graph, but intuitively it's quite clear. And on the assignments, we might see a rigorous proof, I'm not sure. So we are going to assume that this gives you a planar embedding, right? Okay. So this way you can define the plane dual graph. However, the definition written here, if you notice it, it doesn't talk about any drawings. So this is the definition for the abstract dual graph. Right? Okay, so once you have the plane dual, you can take the dual of the plane dual. And the claim here is that by doing so, you will get back the original graph so long as the original graph is connected. And we saw a counterexample when you remove the connectivity condition. So here on the right side, you have a graph G in black color. Its dual is in red. And below, I have drawn the dual in black, and its dual is in red. And you can see that G star star is not the same as G. G is a triangle, K3 and K2 disjoint union, whereas G star star is a K3 and K2 identified at a vertex. Okay. This exercise may or may not be on the assignment. I'm not sure yet. Okay. If it's not, then we are just going to assume it's true. We are not going to really use this fact. So there are a bunch of things that I'm telling you. We are not proving them rigorously. But those things we are not going to really require for further parts of the course, right? So for the proof of Krutowski's theorem, for example, we would not need this fact, right? So I'm not spending too much time on planarity. I want to give it about 2 weeks. And if I start proving all of these things, then we might need something like 4 weeks, right? So, yeah. All right. And towards the end of yesterday's lecture, I mentioned that even if two plane graphs are isomorphic, so that means that the underlying abstract graphs are isomorphic, their duals could be non-isomorphic, right? And one example is here. You have a plane graph with two different drawings. You have a planar graph with two different drawings. And if you draw their duals, you will see that they are non-isomorphic graphs. Okay, good. But notice that what are we doing? How are we going from this drawing to this drawing? We are flipping this triangle along this edge, and this edge is a two vertex cut. So we have this two vertex cut, and we are flipping one component, one S component, if S is the two vertex cut. Like we are geometrically flipping it to get a different drawing. Turns out you actually need a two vertex cut or a one vertex cut to do this. If your graph is three connected, then you actually cannot get two different planar embeddings. So let me just put that, and we will be proving that later in the course. So Theorem 10.28. Every simple, you also need the graph to be simple. You can think about it why, because if you have loops and multiple edges, you can easily get different drawings. Every simple three connected planar graph has a unique planar embedding. Of course, when I say unique planar embedding, that requires some discussion as to what do I really mean by that. So what do I mean by unique planar embedding? I'll take the same example as before, and I will make it three connected. If I add one edge to the previous graph, I get a three connected graph. Now observe that you can no longer do that flip and get a different drawing. What do I mean by different drawing? If you were to label the vertices and edges, then in any planar embedding of this graph G, if you look at the boundaries of the faces and you make a set out of that, in any drawing you will get the exact same set. So what do I mean by unique planar embedding? The boundaries, the face boundaries will be the same for any two distinct planar embeddings. Of course, the way you draw could change. For example, I could draw this graph like this. I can put the two triangles, one inside the other, and this is a different planar embedding, or it looks like a different planar embedding of the same graph. However, if you label the vertices 1, 2, 3, 4, 5, 6, like we had before, you can observe that the face boundaries are exactly the same. And that is what it means for a three connected simple planar graph to have a unique planar embedding. And what this means is that the abstract dual is actually unique, because if you have the same embedding, then the way we define the dual, you're going to get the same graph. So you cannot get two non-isomorphic duals in the case of a simple three connected plane graph. Okay, and thus has a unique dual. Okay, so here I can talk about the dual, although I don't have a plane graph, is because I have a unique embedding. So I'll take that embedding and then I'll take the dual of that, and I can regard that as the dual of the original abstract graph, because for any two drawings I will get the same plane dual, right? Okay, so we will be proving this later. Right now I'm just stating it. Let me just say here, proof later. And intuitively, this is one of the reasons why any proof of the Krotowski's theorem generally reduces the problem to three connected graphs. What this theorem 10.28 intuitively what it is doing is that it's making the representation of the graph, um, it's making, it's allowing you to not consider the representation of the graph. It's telling you that no matter how you draw it, you will get the same face boundaries. And so the representation is now, the planar representation is now unique. And this is intuitively one of the reasons why any proof of Krotowski's theorem first reduces the problem to three connected graphs and then proves it for three connected graphs. Although I think the proof we will see does not really rely on this fact in a concrete fashion, but in some sense, this is playing a role. Okay. Are there any questions or concerns at this point? Anything that's not very clear? Okay, if not, let's move on to something else. Right. Okay. Let me just put down a definition which we might need later. This is a good point to define that. So notice that this graph here, you can add more edges to it while keeping it planar. And the way you would do it is you would take any face of length greater than 3. So let's try to keep the graph simple. Okay. So if I want to keep the graph simple, what I would do is I would take any face of length greater than 3 and add some edges there, so that now all my faces have length 3. And once I have all faces of length 3, it's clear that I cannot add any more edges. I want to keep the graph simple, so I'm not allowing multiple edges and parallel edges, because those I can add as many as I want. So let's not allow those. But if I want to get a simple planar graph with as many edges as possible, I can always do this. I can take a face which has length greater than 3, and I can just add more edges to make all the faces have length 3. Right? And this turns out to be an important concept. In some sense, they are maximal planar graphs. In fact, we will make this precise later. Okay, so let's define these. So a plane triangulation is a simple connected plane graph in which all faces have degree 3. Okay. And what does this tell you about the dual? So I have a question here. What does the dual look like? If all your faces have degree 3 in a plane graph, then what can you say about the dual? What do the degrees of the faces become in the dual? Anyone?
3 connected.
3 is right. Is 3 connected, right? There is something, it has something to do with 3 regular. So because the face, if every face is like a triangle, then in the dual, you will have a vertex here and it will have 3 edges incident at it. It's not actually true, I think. Is the graph going to be 3 connected? I'm not too sure if the graph should be three connected. Actually, should the graph be three connected? If this is a triangulation, we not put two vertices. This is three connected. I don't know if it is necessarily true for the graph to be three connected. It might be worth thinking about that. That one doesn't look so obvious. What is true is that the dual will be a cubic graph. Cubic, also called three regular. Okay. So good. In fact, yeah. In fact, you can prove the proposition. It's if and only if a simple connected plane graph is a triangulation if and only if its dual is cubic. Because for the dual to be cubic, it implies that all the faces would have degree 3. Right? So that's clear. Okay. So that is some fact we might find useful in latter part of the course. Okay. Good. All right. So now let's look at some other cool facts about duality. So one of them has to do with deletion and contraction of edges. Turns out there is a nice relationship between the deletion and contraction of edges. One of the theorems where we saw deletion and contraction of edges is Tutt's wheel theorem, right? We saw that in any three connected graph that is not a wheel, simple three connected graph, you can either delete an edge or contract an edge so that you get another simple three connected graph, which will be smaller than the original graph, right? Turns out that deletion and contraction of edges have more connections in graph theory, and one such instance is planar duality. Okay, so all right, so let me give you an example, and I won't write down the rigorous proofs of some of these things, but the proofs are in the text, and you can probably write them down on your own as an exercise. So what I want to do is, I want to consider what the deletion of an edge looks like and relate it to the dual of the graph. Okay, so stay with me for a bit. Let me take one example. And generally in examples, it's nice to consider non-separable graphs so that all faces are bounded by cycles, but the proof doesn't actually require that. Okay, so when I draw examples, I will often make them look as if all the faces were cycles, all the facial boundaries were cycles. Okay, so let's say I have some graph, and so this is my plane graph, G, and I'm looking at this one edge here. Okay, I want to understand if I delete this edge from the graph, what operations do I have to do in the dual in order to get the dual of the graph after deleting this edge? Okay, so let's draw the dual locally. So of course, this is part of a big plane graph. So in the dual, we will have a vertex here. We will have a vertex here corresponding to this face. And the edges will go out like this, right? So think of each of these segments as one edge. In fact, there was no real need to draw wavy lines. I could have very well made non-wavy lines. Doesn't matter. Okay. And this is your edge E star. Okay. And let's call this vertex F1 star, where F1 is the face in the original graph. And let's call this F2 star. Okay, so what you have in red color is the dual. Now let's suppose we delete this edge E and look at the resulting plane graph. So I'm going to draw G minus E. So let's put the two vertices here. And since I drew wavy lines, let me stick to that plan. Okay, I've got three vertices here, 1, 2, and 3. And I've got two vertices here. Okay, so this is my graph G minus E. What happens in the dual? Well, in the dual, F1 and F2 have combined or merged, if you like, into a single face. All other faces of the graph are the same, right? Of course, there is a possibility that the edge VE was a cut edge, in which case F1 would be equal to F2. But let's not worry about that right now, or consider that as a corner case that you can think about yourself, right? So let's consider the case where E is not a cut edge. Right? So then these two faces combine into a single face. Okay, and let's draw the dual. So now I have a single vertex here, and it has edges like this. What happened? Is there another way to think of the dual? So how can I relate this new red graph, the dual of G minus E? How can I relate it to the original dual G star? We are contracting the edge E star, right? So this is exactly the same as you take the original dual and contract the edge E star. Okay, and well, that is it. And you can turn this into a formal rigorous proof. I won't bother doing that here because it's not going to be really worth our time. Okay, so that brings us to a proposition. Let me state it here because I want to make more drawings. If G is a connected plane graph and E is any edge of this graph G. Oh, okay. So the proposition actually is saying that it is not a cut edge. All right. Then deleting this edge and taking the dual is the same as first taking the dual and contracting the edge E star that corresponds to the edge E. Right? So that is exactly what we wrote down. Okay, I wrote an equal to. I should probably be more rigorous and put isomorphic. Okay, good. So, well, as I said, the proof is there in the text, and it's essentially taking the proof that we saw in these figures and turning it into a rigorous formal argument. It's not too difficult. Okay, good. All right, so that's one thing. What about contracting the edge E instead of deleting the edge E? Okay, so let's do that. What happens if I contract the edge E? Maybe I'm going to make the drawing slightly, okay, good. So if I contract the edge E into a single vertex, then my graph is going to look like this. And now what does the dual look like? Let me draw, maybe put green color. Nah, let me just use red. It's fine. Okay. So now in the dual, I've got a vertex here. I've got a vertex here, same as I had before. The difference is they are not joined by an edge anymore, right? Because the edge separating the two faces has now become a vertex, right? So we don't have a corresponding edge, but we still have all the remaining edges as they were. Right? And how do we relate this dual to the original dual? How are the two duals related? Deletion, exactly. So contracting an edge corresponds to taking the dual and then deleting that edge, right? So here what we have is G contract E, and what we have in red is G contract E dual, which, as you can observe, is the same as first taking the dual and then deleting the edge E star. Okay, and that brings us to yet another proposition. 10.13. G is a connected plane graph. E is an edge. This time, instead of not having it as a cut edge, we are going to not have it as a loop. Okay, so right, because if it was a loop, then contracting the loop would basically be the same as deleting the loop, and then the dual would not really change that much, right? So what would happen in that case? Let's just make a quick drawing to see what happens if it was a loop. If I have a loop, then what would happen is I would have a face here that would be joined to the outside, right? And in the dual, I would have deleted the loop. And in that case, I would basically delete the vertex corresponding to the face of that loop, right? So then you would not have exactly the same relation. Okay, so think about the case when it is a loop. So here we are going to assume that it is not a loop. Okay. And in this case, what we get is that contracting the edge and then taking the dual is the same as first taking the dual and deleting the edge E star. Okay. Again, the proof is not too difficult. It's basically converting what we did in figures into a rigorous proof. Okay. Good. So this tells you that there is a nice relation between contraction and deletion of edges when you look at planar duality, right? So through the lens of duality, you can see that these are connected operations. Okay, good. All right, and there is a theorem that can be proved using these propositions, which I am planning to put on the assignment 3, because it relies on other statements that we did not prove in previous parts of the course. So this will be an opportunity to revisit some of those concepts and connect everything with planarity. So the dual of a non-separable plane graph is non-separable. So this will be on assignment 3. Using preceding propositions. Okay, good. All right. Are there any questions at this point? Also, it's worth noting that if you delete an edge or you contract an edge from a planar graph, you will get another planar graph. I mean, deletion is clear. If you delete, you take any subgraph, the graph will remain planar. What is also interesting and not too difficult to see is if you contract any edge in a planar graph, you will get a planar graph. Okay, so I didn't write that down, but anyways, good. All right, so let's put down some things that we have already observed. So we know that the dual of any graph is connected. This basically relies on the fact that in the plane, you can go from any point to any other point by an arc. And this arc will give you a, a walk between the two vertices or the two faces in the dual. So that's something you can prove easily. We will see a special case of this today. Another thing that follows from the theorem we just discussed, but we did not prove, is that the dual of any loopless two connected graph, which is almost the same as non-separable graphs, is also loopless and two connected. And another interesting fact, which might also be on the assignment, is that the dual of a simple three connected graph, this is not recap, this might be on assignment 3. Is also simple and three connected. Okay. So this is actually exercise 10.2.9 in the text. Okay, good. So I don't want to prove all of these things. Okay. And now I want to do one last thing about duality, which is what I want. I want to connect this with the vector spaces, the cycle space and the bond space that we discussed early on in the course. Okay. And once we do that, we will move on to Euler's formula. And in the next 2-3 lectures, we will be focusing on proving Krutowski's theorem. And the proof will not rely on many of the things that we did not prove here. Okay. So let's do the final part of duality. Let's connect it to the vector spaces that we have already discussed in the course. Any questions or concerns at this point? Okay. So on your assignment 1, if I remember correctly, right? Assignment 1, yes. You proved that the cycle space of a graph and the bond space of the graph, these are orthogonal complements, right? So we saw an algebraic connection between cycles and bonds, or if you like, between even subgraphs and cuts. Turns out that in the case of planar graphs, you can actually see this algebraic connection in a slightly different way, or if you like, in a more geometric or a topological way. Okay, so and it's connected with duality. Okay, so let's go through that part. Okay, good. How do I want to do this? Yeah, let's take an example, and I'll draw one of my standard examples. Okay, so we've got this graph G here. And let's draw the dual. Okay. Now let's consider a cycle in the graph G. Um, well, let's first consider some straightforward cycles. What I mean by that is cycles bounding a face. So if you look at the triangle in this graph, right, and you look at the corresponding three edges, notice that this is a bond in the dual, right? In particular, it is a trivial cut as we defined it on assignment 1. Okay, so every face, it's quite easy to see that that will correspond to a trivial cut in the dual graph, right? Because that face has a vertex, and the boundary of the face is basically going to be all the edges incident at the corresponding vertex in the dual, right? But turns out that something more general is true. So now let's consider a cycle in the graph G that is not a facial cycle, that is not the boundary of a face. Okay, so let's look at that. Supposing I take this cycle. Okay, this is a cycle of length 5, right? That's not the boundary of a face. You can see that inside you've got 2 faces, and on the outside you've got 3 faces. Okay, let's look at the corresponding edges in the dual. So what do I mean by that? Let me draw them in blue color. So whenever an edge is in the cycle, I will take the corresponding red colored edge. So this is one, this is another, this is yet another. Okay, then I've got this, and finally I've got this. Okay, I claim that these 5 edges, they form a bond in the graph G star. Okay, why? Let's think of it intuitively. Okay, let me make a slightly different drawing. So I have a green colored cycle in the original. So supposing this is my cycle in the graph G. What's going on here? Inside, you've got some faces, right? This cycle, you're gonna have some faces inside the cycle, and you're gonna have some faces outside the cycle. Let me not draw them. Let me just draw the ones inside. Okay. In the dual graph, you will have vertices corresponding to each of these faces. The edges of the dual that correspond to cycles that correspond to edges of the green cycle will basically be edges that go like this. Okay. Of course, there could be more. There could be more vertices, but doesn't really make any difference. Supposing there was a vertex here, then you would have 2 edges like this. Okay. But what's going on is that you are looking at all the edges going from vertices that are inside the cycle, vertices of the dual that are inside the cycle, to vertices of the dual that are outside the cycle. Right? And that's a cut. That is a cut in the dual. You have a partition of the vertex set. You look at all the vertices inside the cycle, that's one part, and all the vertices outside the cycle. I'm talking about dual vertices. And all of the blue colored edges are edges that are going from the inside dual vertices to the outside dual vertices. And any edge that joins 2 vertices in the inside will not be part of your set. Okay, so you won't have any edges that are joining 2 vertices, 2 dual vertices inside the cycle, or 2 dual vertices outside the cycle, right? So every edge will join a vertex inside to a vertex outside. And that is exactly what a cut is, right? The only thing we need to prove is that the inside is a connected graph in the dual and the outside is a connected graph in the dual, right? Because if they both are connected, then we know that the cut is a bond. Okay, is it intuitively clear what's going on? Why are cycles becoming bonds and vice versa? Well, we didn't discuss the vice versa, but you can imagine that it's going to be true as well. Okay. All right. So that's the first statement we are going to prove. Okay. So we are going to prove the following theorem. 10.16. We will prove only one part of it, and the other one is either do it yourself or it might be on the assignment. So it's basically looking at orthogonality of these vector spaces via the lens of duality. That's a good way to label this theorem if you like. So you take any connected plane graph and you look at its plane dual. So it's important that instead of the abstract dual, we are referring to the plane dual. Okay, so the plane dual of G. Okay, then the following are true. If C is a cycle of the plane graph G, then the corresponding edges C star, right? So what I mean by C star, it's the set of all edges E star such that E belongs to the cycle C, right? We are viewing cycles and bonds as sets of edges. Okay, then C star is a bond of the dual. Okay, and secondly, if B is a bond of G, then B star, defined the same way as we define C star, is a cycle of the dual plane graph. Okay, good. All right, so we'll write down the proof of this. But remember, one of the things we need is so we have to show that it is a cut. So we are going to show part A. We are going to take a cycle in the graph G, like we did in our example, the green colored cycle. And then we are going to look at the blue colored edges corresponding to that cycle in the dual. We want to prove that that is a bond. In particular, we need to show that it is a cut and that the two sides of the cut are the induced connected subgraphs in the dual. Okay, so that requires us to prove the following proposition. You take a plane graph G and you take its dual, plane dual. You take a cycle of the graph G and let X star be the set of vertices, set of dual vertices that lie in the cycle, that lie in the interior of the cycle, right? So it's basically, in our drawing here, X star is all the red colored vertices that I drew. Okay, in our example, there will be these two vertices. Okay, good. Then the claim is that the graph induced by X star, the dual graph, yeah, it should be the dual graph, is connected. Okay. So how do you prove this? Well, the idea is as follows. So you've got this, let me make a different drawing, repeating the same one as before. You've got this cycle in the plane graph G, and you're looking at all the vertices of the dual that are inside it, right? This is your set X star. So what we are going to do is, notice that in the plane, if you take any such closed curve, right, you will be able to connect them. You will be able to connect any two vertices by an arc, right? So this is basically Jordan curve theorem. You have the interior of the cycle and you have the exterior of the cycle or of the closed curve, right? And both of these are arc-wise connected. What that means is that for any 2 points, you can find an arc connecting them. In particular, if you take two red vertices in your set X star, then there is an arc joining those two red vertices that does not go through any other red vertices, because the red vertices are finite. So you're always going to be able to join the two red vertices without going through any other red vertex or any other red point. And you look at this arc, and this arc will basically be crossing some face boundaries. And that will give you a walk in the dual between the two corresponding vertices. It's basically the same reason why the dual of any graph, whether it is connected or not, is connected. So this exact same argument is used to prove this proposition, right? I won't write down the formal rigorous argument here, right? But the idea is, you know that there is an arc joining the two red points, and you look at this arc, it will have to go through some face boundaries because they correspond to two different faces. And this will give you a walk in the dual graph joining the two red vertices. And if you have a walk joining the two red vertices, then you have a path joining the two red vertices. In particular, the dual induced by X star is a connected subgraph. Okay? So that's that. Okay? It simply relies on formalizing this argument. Okay? And I'll just make a note here. It's the same reason why the dual of any graph, any plane graph, is connected. Okay, good. And now we can proceed to prove part A of this theorem. And part B, I'll just leave it to you, or I'll put it on the assignment. All right, so let's take a cycle. And let's take the set of vertices of G star that lie in the interior of the cycle, right? And observe that C star, so the edges corresponding to that cycle, is exactly the edge cut partial of X star in G star. Right? You go back to this drawing. So all the edges corresponding to that cycle are exactly those edges which join that join an interior face, the face in the interior of the cycle, to a face in the exterior of the cycle. Right? Those are exactly the edges that will be crossing the cycle as per our plane dual definition. Right? So it is a cut, and now, since the interior is connected by proposition 10.15, notice that the interior and exterior, they are the same. We have discussed this before. So the exterior is also going to be a connected subgraph. And since both of them are connected, the cut is a bond. By proposition 10.15, the graph induced by these vertices is connected. And likewise, the graph induced by the vertices of the dual minus x star, so the complement, is also connected. And so C star is a bond in the dual, right? So we have a cut, both sides are connected, that's a bond. Good. All right. So, well, this is basically all I want to tell you for now about planar duality, right? And on Thursday, we will quickly go through Euler's formula. I believe you have all probably seen Euler's formula on your previous courses. So I will not go into it in too much depth, right? We will go through it really quick. And once we finish that part, we will move on to proving Krotowski's theorem using the theory of bridges. So we will be spending some time on the theory of bridges, and then in another lecture or two, we will go through the proof of Krotowski's theorem. Okay, good. Any questions or concerns? Yeah, so the lecture is officially over. Feel free to leave the meeting. But if you have any questions or concerns, please go ahead.